Hey, welcome. Have you ever stopped to wonder what actually makes artificial intelligence, well, intelligent? It's not some big magic trick. It's really a series of building blocks. And today, we're going to dig into the most fundamental one of all, the AI agent. First, let's tie this whole idea to some tech you probably use every day. So, take a look at these three. A Roomba, Siri, a self-driving car. One cleans your floors, one lives in your phone, and the other, well, it drives itself. What on earth could they have in common? Believe it or not, the thing that ties them all together is that at their core, they are all AI agents.
And here's the official definition. I know, it sounds a little dry, but it's actually super simple. An agent perceives the world around it with its sensors. That little snapshot of data it gets at any given moment, that's called a percept. So for a self-driving car, a percept is just the camera data saying, hey, there's a stop sign. For Siri, it's the sound of your voice. Then, the agent acts on the world using its effectors, things like motors or wheels or a speaker. So the car senses the stop sign and its effectors hit the brakes. Siri senses your voice and its effectors spits out a reply. That's the loop right there. Sense and act.
Okay, but an agent isn't just floating around, sensing and acting for no reason. It's built for a purpose. It has a job to do, a problem it needs to solve. And to do that job, it has to understand the world it's living in and, the rules of the game.
And these jobs are all over the place. An agent's job might be something like classification, looking at an email and deciding spam or not spam. Or maybe it's doing reinforcement learning, where an agent literally teaches itself how to beat a video game just by playing it over and over. Every single one of these tasks needs its own special kind of agent.
So, before an agent can solve anything, it needs a map of its world. And in AI, we call this map the state space. It's basically the set of every single possible situation the agent could ever find itself in. Forget chess for a second. Just think about that Roomba. Its state space is every single spot it could be in your room, combined with every possible crumb of dirt on the floor. It's this huge, invisible map of possibilities.
And on that massive map, our agent has to start somewhere. That's the initial state. For our Roomba, it's pretty simple. It's sitting on its charging dock, and the room is a mess. That's square one.
And of course, if there's a starting line, there has to be a finish line. The goal state is what our agent is desperately trying to achieve. For the Roomba, the goal is a perfectly clean floor and getting itself back to the charger. That's the win.
So how does it actually get from the messy room to the clean one? It uses operators. These are just the legal moves it's allowed to make to change its situation. For the Roomba, the operators are pretty basic. Move forward, turn left, turn right, and turn on the vacuum. By using these moves, it navigates through its huge state space from the start all the way to the goal.
All right, so we get it. The agent has a map, a start, a finish, and a set of moves. But how does it decide which move to make? How does it actually figure out its path to victory?
Well, it thinks using something called a search tree. Just picture it starting at the top of a giant branching tree. Every possible first move it could make is a new branch. And from the end of those branches, every possible second move creates even more branches, and on it goes. The agent basically explores all these different branching paths, looking for the one that gets it to the goal state the fastest. This is how it plans.
Now, planning with a search tree is a really powerful idea. But here's the thing. Not all agents are created equal. Just like in nature, AI agents have evolved, getting smarter and more capable over time. So now we're going to climb that ladder of complexity, starting with the most basic agent and going all the way to the top.
Here's our path up the ladder. We'll start at the bottom with the simple reflex agent, and we're going to climb all the way up to the learning agent, which is an agent that can actually teach itself new tricks.
So at the very bottom of the ladder, we have the simple reflex agent. This thing is purely reactive. It follows one simple rule. If this happens, then do that. A thermostat is the perfect example. If its sensor perceives the temperature is below 70 degrees, then its effector turns on the heat. Simple. It has zero memory of the past. It only knows what's happening right this second.
The next step up is a huge leap. This is the model-based agent. This agent actually has a kind of memory. It builds an internal model of how the world works, based on everything it's seen before. And this is a game changer because it lets the agent understand what's going on even when it can't see everything at once. Like a self-driving car, knowing another car is probably still in its blind spot, even if the sensor loses sight of it for a split second.
And this slide just lays it out perfectly, right? The simple agent is totally stuck in the present moment.
But the model-based agent can use its memory, its internal model of the world, to understand context and work in much more complex environments where it doesn't have all the information. So the key difference, the big evolutionary jump, is memory.
Okay, let's keep climbing. The goal-based agent has everything the model-based one has, plus one absolutely critical addition: a purpose. And this changes everything. It's not just reacting or understanding anymore. It's actively trying to achieve something. It can actually plan ahead, thinking, okay, if I do this and then this, will that get me closer to my goal? That ability to plan is what makes an agent truly proactive.
But what happens when there are a bunch of different ways to reach a goal? That's where the utility-based agent comes in. See, this agent doesn't just want to win. It wants to win in the best way possible. Is one path faster, or safer, or more efficient? It uses something called a utility function to basically score the different outcomes and pick the most desirable path. Think about your GPS picking the fastest route home, not just any route that will eventually get you there.
And here we are at the top of our ladder, the learning agent. This is where things get really, really cool. This agent isn't stuck with the programming it started with. It can get better, on its own. It starts with some basic knowledge, and then, through trial and error, it learns from its own successes and failures to improve its performance over time.
The best way to think about it is like you're learning to play basketball. The performance element is you actually taking a shot. The critic is your coach on the sidelines, giving you feedback like, hey, great form, or you missed wide left. The learning element is your brain, taking that feedback and adjusting your strategy for the next shot. And the problem generator? That's the coach saying, okay, now try it from the three-point line, pushing you to try new, harder things to expand your skills.
So we've climbed all the way from a simple thermostat to this complex, self-improving system. But look, this isn't just theory from a textbook. These agents are all around us, right now, in the real world.
What's so interesting here is seeing how real-world tech mixes and matches these agent types. Siri is goal-based. Its goal is to find an answer for you. And it's a learning agent because it gets better at understanding you over time. A self-driving car absolutely has to have a model of the world. It uses utility to find the safest route, and it is constantly learning from every single mile it drives. We're literally interacting with this whole evolutionary ladder every single day.
And that brings us to one final really important question. We've managed to build these incredible agents that can sense and act and plan and even learn all by themselves. The journey from a simple on-off switch to a learning machine has been pretty incredible. So the only question left is, what's the next goal we're going to give them? And that question is what will define the entire future of AI. Thanks for joining me on this journey.